Hello everyone. On this video we will be going over definite integrals when they involve left and right endpoints. Okay, so we're kind of going to piggyback off of the formula we use to find the area of a function. Okay, so if you remember, the area is equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of c plus c sub I delta x. And that's where your c sub I is between your A and B, your left endpoint and your right endpoint. Okay, so this is true only if your function is continuous and non-negative. Okay, so we kind of went over that with the previous video. All right, so from here, we're going to go right into the definition of a definite integral. Okay, which I've written down already. Okay, kind of separate that a little bit. Okay, so the definite integral of f of x on the interval between x is between a and b is denoted by this here. You have your integral from a to b of f of x with respect to x. And that is the limit of the Riemann sum as n approaches infinity. Okay, so what that means is all of our rectangles, when we were looking for the area, we're just saying as we get almost an infinite number of rectangles, that will be our Riemann sum. Okay, so in other words, what this definition says is that if you get your integral from a to b of your function of x with respect to x, that's going to equal the limit as n approaches infinity of that first rectangle, the height of that first rectangle, the second rectangle, third rectangle, all the way to some nth rectangle, because n's getting really, really, really big, times the width, which is your delta x. Okay, which simplifies to the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I delta x. That's why I was saying that if you want, you can use, instead of c sub I, you can use x sub I. We could have used c sub 1, c sub 2 here, but we just chose to use x sub I because we're going into the Riemann sum, and it's kind of a little bit different than when we were just looking for the area. So that's why it's kind of the x sub I instead of the c sub I, but it's pretty much the same thing. All right, just a change in variable. Okay, now for your definite integral, the parts of your definite integral, you have your function of x, that's called your integrand. Okay, your a, that's your lower limit of integration. Your b is, of course, your upper limit of integration. And your dx, that indicates with respect to x, which means x is your integral of your variable of integration. Now, some of you may say, well, that seems kind of obvious. Well, it's obvious now, but as you move ahead in calculus, you're going to have some functions that will have 3, 4, 5, or more variables. And you may not have to integrate with respect to all of those variables. You may only have to integrate with respect to x, or with respect to r, or with respect to s, or with respect to t. So that dx is actually very important, but it doesn't become as crucial until later in calculus. So it's best to kind of get an understanding as to what that dx means now, because it will help you later. All right. So if you, I know I rewrote this or pre-wrote it. So if you are still writing this down, by all means, feel free to press pause. But we're going to go ahead and move on to our first example. All right. So let's say for our first example, we want to find the limit definition and by limit definition, you may also see some problems. Say you want to find, also known as, the limit of sums. Okay, so if you see a problem that says the limit definition or the limit of sums, it's the same thing. Okay, so we're going to find the limit definition, also known as the limit of sums, of the definite integral and that definite integral is the integral from 7 to 13 of 4x to the 5th power with respect to x using a right endpoint Riemann sum. All right, now I know some of you may actually know how to use the fundamental theorem of calculus on this problem and figure, okay, well, I'll just take a shortcut and use that. You won't be able to do that for this type of problem. Okay, because if you do just the fundamental theorem, then you will end up with a completely different type of answer. Okay, so we're actually looking for the limit definition or the limit of sums, which means you're going to have to go through either these steps that I'm going to show you or through steps that are proven to be correct. Okay, so once again, you can go through these steps or you can find steps of your own that actually work, and I'm okay with that. Okay, so let's go with our first step, which is find your delta x. Okay, so we know when we see our integral from 7 to 13, that's the same as saying our interval from 7 to 13. Okay, so we know that just from the previous video that 7 represents your A and that 13 represents your B. Okay, so we know that our delta x is equal to B minus A over N, which is 13 minus 7 over N. Okay, now this one's a little different than our area because our area video, because if you remember, we had on our area video, it said we want 4 subintervals or 5 subintervals or 6 subintervals. So we knew that n would equal that 4, that 5, or that 6. Here, n is approaching infinity. So we don't have a value for n. So we just end up with 6 over n as our delta x. Okay, so that's how this is a little bit different. Okay, so now we move on to our second step. Okay, where we find the function at the right endpoint. Find the function at our right endpoint. Okay, now to do that, here we have our endpoints. Here we have our 7 and our 13. Those endpoints, we just have a general formula for those. That's x sub I minus 1 and x sub I. Okay, so let's say I is equal to 3. You have x number 3 and our second x value. Okay, or if I was equal to 7, you'll have our 7 and 7 minus 1, which is 6. So it'll always just be that little interval there. So our x sub I minus 1 is our left. And our x sub I is, of course, our right. All right, so if you have your x sub I, that has its own formula. Your x sub I is going to equal your x sub 0, which is your starting value, plus I delta x. Okay, so this is your right endpoint formula. Okay, so whenever you have a problem that has the right endpoint, This is the formula you're going to use. And I'm going to do another example where it shows your left endpoint. Okay, so we know between 7 and 13, we're going to have a bunch of values in between there. A bunch of rectangles, I guess you could say that. Okay, so your A is your x of 0. And then it's just going to keep getting bigger and bigger and bigger. So that x of 0 is going to be less than your x of 1, which is going to be less than your x of 2, which is going to be less than your x of 3. And it keeps on going. It's going to be less than your x of n minus 1, which is less than your x of n, which is actually your b value. Okay, so here your a is equal to x of 0. So your a is equal to x of 0. So we plug in the x of 0 in this formula. Okay, so your x of I is going to equal 7 plus I delta x. So that's I, and your delta x is 6 over n. Okay, so if we go ahead and simplify that, and what I like to do, and you can have a completely different method if you like, I like to have my x of I as just one neat little quotient. Okay, I don't like having a whole number here and a quotient here. I try to have it as one neat little quotient. So if you remember that 7, you can make that 7n divided by n, because if you simplify that by canceling those n's out, you just end up with 7. Okay, you actually end up with 7n over n plus 6i over n. So you can combine those. You have x of I equals 7n plus 6i over n. Okay, so this is our x of I. Okay, so we're going to need that. All right, so we're not quite done with our second step yet, because once we find our x of I, we have to find our f of x of I. Okay, so moving on, we know that our f of x is 4x to the 5th power. So f of x equals 4x to the 5th power. Okay, so that means our f of x of I is just going to be 4x of I to the 5th power. Let me clean that up just a smidgen. All right, but we already know that our x of I is equal to 7n plus 6i over n. So that means your f of x of I is going to equal 4 times 7n plus 6i over n to the 5th power. Almost ran out of room. All right, now me personally, I'll just try to get rid of that exponent, so I distribute it to both of those, which gives us an f of x of I is equal to 4 times 7n plus 6i to the 5th over n to the 5th power. Again, you can leave it like that. That'll be fine, but I personally like to just get rid of that exponent. Okay, so here we have our function at the right endpoint. Okay, that's not our limit definition, but it gets us really close. This is just our function at the right endpoint. It's not our limit definition just yet. That brings us to our third step. Okay, let me kind of separate that a little bit. So your third step is where we use our definition of a definite integral. Okay, so that's the limit as n approaches infinity of the sum from I equals 1 to n of f of x of I delta x. That's our definition. Okay, now, thing is, we know what our f of x of I is. We just solve for that, and we know what our delta x is. We solve for that. So we go ahead and replace those two. So that's the limit as n approaches infinity of the sum from I equals 1 to n of f of x of I, which is 4 times 7n plus 6i to the fifth over n to the fifth power times delta x, which is 6 over n. All right, so just to kind of clean it up a little bit, I'm going to go ahead and multiply this 6 and the 4 and multiply these two n's. That gives us the limit as n approaches infinity of the sum from I equals 1 to n of 6 times 4, which is 24. And you have n to the fifth times n to the first, which is n to the sixth power. So I'll just make that 24 over n to the sixth power. Times, you still have your 7n plus 6i to the fifth. And this is your limit definition. Also known as your limit of sums. Okay, so this is why if some of you plan to just use the fundamental theorem, it wouldn't quite work out because your answer is completely different. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next example. All right, so for this example, let's say we wanted to use the definition of a definite integral to evaluate the integral from 3 to 8 of 8x with respect to x using left endpoints to generate the limit of sums and Riemann sum. Okay, so we're looking for two different answers here. But actually, we're going to encounter the limit of sums as we solve for the Riemann sum. So it's really just identifying the limit of sums on our way to solving the Riemann sum. All right, so the first three steps are identical to the example we just did. Okay, so we can go ahead and start that. So your first step, you're going to find your delta x. Okay, and we use our integral right there. So we know that the integral from 3 to 8 is just the same as the interval from 3 to 8. Okay, so we know our 3 is our a, and our 8, that's our b value. So we know that, not x of 0, delta x is equal to b minus a over n. Okay, which is 8 minus 3 over n, which gives us 5 over n. Okay, so we have our delta x. All right, so now we go to our second step where we find the function at left endpoints. Okay, so for our second step, we want to find the functions at the left endpoints. All right, so just like the previous example, we have our x sub I minus 1 and our x sub I to represent our left and our right endpoints. Okay. Now this time, if you notice on the previous example, we had our x sub I formula. I'm going to make a little note for this. So note okay, so your right endpoint is x sub I equals x sub 0 plus I delta x. Okay, that's what we used on the previous example. For this example, we're looking for the left endpoint. So that's our x sub I minus 1. And that's going to equal x sub 0 plus I minus 1 times delta x. So as you can see, it's pretty much the same formula. You're just, instead of I, you're going to have I minus 1 next to your delta x. Okay, so this is your left endpoint formula for x sub I minus 1. Let me clean that A up a little. There we go. Okay, so that's our left endpoint formula. Okay, so just like before, you know, our A is equal to our x sub 0, which is less than your x sub 1, less than your x sub 2, which is less than your third x value, and it keeps on going all the way till you get to your nth x value, which is our B. Okay, so we know that our A is equal to x sub 0. So we plug that into our formula. Okay, so that means your x sub I minus 1 is equal to x sub 0, which is 3, plus I minus 1 times delta x, which is 5 over n. Okay, so just like before, if you wanted to, you could leave it like that. I just try to simplify it a little bit. Remember that your 3 is equal to 3n over n. So that means your x sub I minus 1 is equal to 3n plus 5 times I minus 1 over n. Okay, so we have our x sub I minus 1. All right, so just like before, we're not done with step 2 yet. Okay, we know in this case our f of x is equal to 8x. So that means our f of x sub I minus 1 is just equal to 8 times x sub I minus 1. Just replacing the x with x sub I minus 1. Okay. But we know what our x sub I minus 1 is equal to. It's equal to this. So that means your f of x sub I minus 1 is equal to 8 times 3n plus 5 times I minus 1 over n. And this is our function at the left endpoint. Okay, it's not our limit sum yet. We haven't gotten to our limit sum, but it is our function at our left endpoint. All right, so now we move on to our third step, which will show us our limit sum or limit definition. Okay, so your third step, which shows the limit sum, we have the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I minus 1 delta x. Alright, so we know our f of x sub I minus 1, and we know our delta x right up there. Okay, so that's going to equal the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I minus 1. So that's going to be 8 times 3n plus 5 times I minus 1 over n times delta x, which is 5 over n. Okay, so we can go ahead and simplify this. We can go ahead and multiply that 8 and that 5. We can multiply your n's there. So that's going to equal the limit as n approaches infinity of the sum from I equals 1 to n of 8 times 5, which is 40, over n times n, which is n squared, times 3n, plus, we can go ahead and distribute that 5. Might as well do that now. Plus 5i minus 5. Okay, now this is your limit of sums. Or your limit definition. Move that up a little bit. Okay, so we're done with the limit of sums. We found that. Now we keep on going to find our Riemann sum. So we're going to continue that on the next page. So if you are still writing, feel free to press pause. But we're going to go ahead and finish this up on our next page. All right, so we're going to go ahead and continue. All right, so I'm just going to write where we left off on the previous page. So that's the limit as n approaches infinity of the sum from I equals 1 to n of 40 over n squared times 3n plus 5i minus 5. All right, so what we're going to do is we're going to take our summation and our 40n squared, and we're going to distribute it to each term. Okay, so that's going to equal the limit as n approaches infinity of the sum from I equals 1 to n of 40 over n squared times 3n, because we're getting this whole thing multiplying by 3n. Then we're going to take this whole thing multiplied by 5i and this whole thing multiplied by negative 5. Okay, so that's plus the sum from I equals 1 to n of 40 over n squared times 5i minus the sum from I equals 1 to n of 40 over n squared times 5. All right, so now what we're going to do, we're going to simplify each of those terms. And we're really just looking for the terms with the i's to keep in front. Anything without the I, we're going to move it. Okay, so you have the limit as n approaches infinity. Okay, so here you have the n's, one of those n's cancel out. 40 times 3 is 120. So you have the sum from I equals 1 to n. You have 120 over n, but you can bring that 1 over n out to the front. Okay, so that's plus the sum from I equals 1 to n. Oh, let me move that over a little bit. You have 40 times 5, which is 200, so that gives you 200 over n squared. So you have 200 over n squared. And our I, actually, let me clean that up just a little bit, give it a little more room so it's not all congested. So the sum from I equals 1 to n of I. Okay, so that's minus, you have 40 times 5, which is 200. So you have 200 over n squared. Now, if you want, I'm going to show you a way to do this one a little different than the first term. Sum from I equals 1 to n of 1. Okay. Now, if you wanted to, you could have definitely kept the 200 in front. It wouldn't have made a difference. I just show you that you could have factored out the 120 over n here and put that as a 1. You could have made this 200 and had the 1 over n squared here. It wouldn't have mattered either way. I just want to show you multiple ways to handle the same situation. All right. Okay, so what we're going to do here is you have to kind of go back in your memory a little bit. Okay, and remember our summation. So you have the sum from I equals 1 to n of I. Remember, that's equal to n times n plus 1 over 2. And the sum from I equals 1 to n of just a constant is equal to n times that constant. All right. So what we're going to do is we're going to simplify each one of those summations. So you have the limit as n approaches infinity. The sum from I equals 1 to n of a constant is just n times that constant. So you have 1 over n times that constant, which is 120 times n. Okay, so plus you have 200 over n squared. Remember, the sum from I equals 1 to n of just I is n times n plus 1 over 2. So that just gets replaced with n times n plus 1 over 2. Okay, so that's minus 200 over n squared. And the sum from I equals 1 to n of a constant is just n times that constant. So that's just 1 times n, or just n. Okay, so we simplified each individual term using our summation. All right, so let's go ahead and simplify these a little bit further. So you have the limit as n approaches infinity. I'll bring this up a little bit. Okay, so you can see here the two n's cancel out, so you're just left with 120. Plus the 2 and the 200 kind of simplify, so you're left with 100. So 100. And the n and the n squared kind of simplify, so that's 100 over n, so that's 100 times n plus 1 over n, minus the n, and one of the n's in the denominator cancels out, so you're left with 200 over n. Okay, so we're going to go ahead and distribute that 100. So that's equal to the limit as n approaches infinity of 120 plus you have 100n over n plus 100. 100 times 1 is just 100 over n minus 200 over n. All right, so that will give us the limit as n approaches infinity of 120 plus, here your two n's will cancel out, so that would be 100 plus, you have 100 over n minus 200 over n will give you negative 100 over n, so that actually should be minus. It's minus 100 over n. So just to go ahead and combine those to simplify it, you have the limit as n approaches infinity of 120 plus 100, which is 220, minus 100 over n. Okay. So which brings us to our fourth step, which is just to distribute your limit. As n approaches infinity. Let's bring that up a little bit more. There we go. So if we go ahead and distribute that, we end up with the limit as n approaches infinity of 220 minus the limit as n approaches infinity of 100 over n. Okay, so we know that the limit of a constant is just that constant. So you have 220 minus, so you have the limit as n approaches infinity of a constant over an infinite or approaching infinite value is just going to be 0. So you end up with 220 as your Riemann sum. All right. So if you are still writing, by all means, feel free to press pause. But we're going to go ahead and do one more example. All right, so for this example, what if we wanted to use the definition of the definite integral to evaluate the integral from 0 to 2 x squared with respect to x. Okay, so you want to use the right endpoints to approximate, or right endpoint approximation, sorry about that, to find the limit of sums and generate the Riemann sum. Okay, so the first three steps are just the same as our first example when we use the right endpoints. So what I want you to do is I want you to go ahead and press pause and try to solve this one on your own. All right, so I'm assuming you've pressed pause and you've worked this problem out on your own. So let's go ahead and verify your answer. Okay, so of course our first step is to find your delta x. Okay, so we know our integral here, our integral from 0 to 2 is the same as saying our interval is from x equals 0 to x equals 2. So we know that that's our A and that's our B. So that means our delta x, which is b minus a divided by n, is equal to 2 minus 0 divided by n, which is just 2 over n. Okay, so that's our delta x. Okay, so we go ahead and move to our second step, which is to find the function at the right endpoints. Okay, so find our function at the right endpoint. Okay, so once again, we know that our left and right endpoints are x of I minus 1 and x of I. So that's our left and that's our right. So since we're looking for the right endpoint, we're going to use our x of I is equal to x of 0 plus I delta x. Okay, remember that's your right endpoint formula for x of I. Okay, remember your left input formula is a different formula. You're basically replacing the I with I minus 1. But for your right endpoint, you have your x of I. Okay, so if we go ahead and remember that your A is equal to your x of 0, we know that x of I is equal to 0, since that's your value of x of 0, plus I delta x, which is 2 over n. Okay, so if we simplify that, that means our x of I is equal to 2i over n. Okay, so we'll go ahead and mark that since we're going to need it. And again, that's just the first part of our second step. We now have to find our function. So here, your f of x is equal to x squared. So f of x is equal to x squared. So that means your f of x of I is just equal to x of I squared. Okay, so we know our x of I is 2i over n. So our f of x of I is going to equal 2i over n squared. Okay, so if we go ahead and distribute that squared, it's going to equal 4i squared over n squared. Okay, now this step you want to be really careful on because it's really, really easy to make a mistake and say, oh, this is just 4i over n squared or something like that. You don't want to make a little minor mistake to throw off your whole problem. So whenever you have exponents, you want to be really careful with when you distribute them. Okay, so remember, this is your function at your right endpoint. All right, so we go ahead and go to our third step where we find our limit of sums or limit definition. Okay, so our third step, our limit of sums. Okay, so we know that the definition for that, you have the limit as n approaches infinity of the sum from I equals 1 to n of f of x of I, it's x of I since we're using the right endpoint, delta x. All right, so that's going to equal the limit as n approaches infinity of the sum from I equals 1 to n of f of x of I, remember that's 4i squared over n squared, times your delta x, which is 2 over n. All right, so if we go ahead and just combine those, we end up with the limit as n approaches infinity of the sum from I equals 1 to n. 4 times 2 is 8, so that's 8i squared over n squared times n, which is n to the third. Okay, so that gives us our limit of sums, also known as our limit definition. All right. So we're going to continue this on the next page. So if you are still writing, feel free to press pause, but we're going to go ahead and finish this one up. All right. So let's just write down where we left off. So you have the limit as n approaches infinity of the sum from I equals 1 to n of 8i squared over n to the third. Okay. Now, before we continue, you want to remember one important thing, and that's the sum from I equals 1 to n of I squared is equal to n times n plus 1 times 2n plus 1 over 6. Okay, so that's going to be important to solve this particular problem. Okay, so we're going to get all of the terms that don't have an I. So we're going to get the 8 and the n to the third, and we're going to move that out to the front. So you have the limit as n approaches infinity of 8 over n to the third times the sum from I equals 1 to n of I squared. Okay, so now we're going to replace this sum with this term here. So that's the limit as n approaches infinity of 8 over n to the third times n to the third power times n plus 1 times 2n plus 1 over 6. Okay, so now what we're going to do is we're going to go ahead and distribute. Well, first we have to FOIL these two and then multiply each one of those terms by n. So once you do that, the limit as n approaches infinity of 8 over n to the third, that's going to equal 2n to the third plus 3n squared plus n all over 6. All right, so now we're going to go ahead and get that 8 and distribute it to each term. So you have the limit as n approaches infinity of 16n to the third plus 24n squared plus 8n all over 6 times n to the third, 6n to the third. All right, so if we go ahead and just break these down to 3 separate terms, it'll make it a little bit easier. So you have 16n to the third over 6n to the third plus 24n squared over 6n to the third plus 8n over 6n to the third. All right, so I just went ahead and broke it down just to make it a little easier to simplify. Okay, so that's going to equal the limit as n approaches infinity. 16n to the third over 16 to the third, that simplifies to 8 over 3. Plus 24n squared over 6n to the third, that simplifies to 4 over n. Plus, you have 8n over 6n to the third, that simplifies to 4 over 3n squared. Okay, which brings us to our fourth step where we just distribute our limit. Okay, so if we go ahead and distribute our limit, you have the limit as n approaches infinity of 8 over 3 plus the limit as n approaches infinity of 4 over n plus the limit as n approaches infinity of 4 over 3n squared. All right, so we can see here that as n approaches infinity, this term becomes 0 and this term becomes 0. So you have the limit as n approaches infinity. Oh, actually, you don't need that because the limit of a constant is just that constant. So this just becomes 8 over 3 plus 0 plus 0, since both of these limits are equal to 0, which gives you a final answer of just 8 over 3. All right, so with these problems, the individual steps are sometimes not that bad or not as bad as others. The individual steps may not be bad. They may be a little tedious and a little bit long, but overall, the individual steps are not what requires the practice. It's doing the first step, then the next step, then the next step, then the next step. So the practice is required for doing all the steps in order. Okay, that's what you want to practice on. The individual steps, the first 3 steps are usually not too horrible. It's that, when you get down to simplifying all of this, is just, mostly paying attention to detail, not trying to make that little error. Those are the things you want to watch out for. But all in all, if you're still having trouble, rewrite these particular questions, these example questions. Rewrite them, try to solve them. Make sure you know, okay, this is the process, because it helps a lot to rewrite the steps and really drill the steps into your head. All right, so hopefully this made sense, and I'll see you on the next video.